Welcome back, everybody, to the special seventh period edition of a video today. I took a video in my second period class, and no, I didn't leave it running. It just, my computer just died during it. My swap. But I got my computer back. Got my computer back now. Hey, Alex, you're okay.
Ooh, I'm a go.
Shouldn't make deals with the devil.
Ooh, I'm a go.
Hear that? That's recorded. Corbin. So let's talk about what do you
Do you use that over Christmas break at all?
Yes, I do. Don't touch it. So just to kind of talk about the schedule here. We did section 3.1 on Wednesday and Thursday. We're going to do section 3.2 today. We're going to be able to get to the whole thing today. Okay? Monday is the work day over both of those sections. Okay? I will answer questions over 3.1 on Monday if you'd like to. I could go over a bunch of them if you need to. But 3.1 I'm going to have due at midnight on Monday, and then 3.2 I'll have due midnight on Tuesday. I've decided to do that. Okay? So 3.1 will be due on Monday night, 3.2 will be due on Tuesday night. We are going to start new notes over section 3.3 on Tuesday. Okay? Just so you're all prepared.
So we have a work day on Monday.
Right. So work day is Monday.
Good job, Dakota. Way to think that one.
Okay, so again, we are in this mode of trying to create ways that we can bypass the definition of a derivative, right? That's what we're going to be looking at today. We're still pushing forward in trying to find ways to bypass the definition of a derivative. My computer's going to die if I don't plug it into. So what we're going to be looking at today is how we could multiply or divide functions.
I think the charger's already over here.
I need this to be able to take the derivative. Okay? Multiply or divide functions to be able to take the derivative. And that's the old one, right? Got the USB-C charger stuff.
Oh, fancy. I don't know why they made those.
Oh, yeah.
USB-C?
They're better.
It's faster.
Yeah, they're better.
Did you hear Europe is actually going to pass a law that everything must be charged using the same connector. So like Apple products, everything has to be charged by USB-C.
What's the reason behind that?
To make
So you
it
can't monopolize chargers
right,
Apple.
like Apple does. So what we're going to be looking at today is the product and quotient rules. We're going to be able to multiply and divide. So let's start with the product rule. You know, it's interesting to point out that when Leibniz started first making these rules about calculus, like he was the first one to talk about the sum rule and the difference rule, but he theorized, back before he knew, he theorized that just because we had just because we had d over dx of f plus g was d over dx of f plus d over dx of g, he was like, well, it makes sense to state that if this is true, he was like, I bet this is true too. Okay? And he was like, I think that's true, but a very basic example can be a counterexample. For example, let f be x and let g be x squared. So that would make d over dx of x times x squared be d over dx of x, d over dx times d over dx of x squared. Well, what is d over dx of x? What's the derivative of x? 1. What's the derivative of x squared? 2x. So we said, okay, I bet it's 2x then. Is that really true? What is x times x squared? X cubed. What is d over dx of x cubed? 3x squared. So this is definitely not true. That's a basic counterexample to show that this, wrong, can't do that. So what is the rule for multiplication? And this is the rule for multiplication down here. Okay, I'm going to try to simplify it a little bit. I'm going to get this out of the way first, though. I'm going to try to simplify it a little bit for you, but this is it in Leibniz notation. It's good to kind of look at that just to see it. D over dx of fg, f times g, is f of x times the derivative of g plus g of x times the derivative of f. Okay, in our notation here, if you've got f times g prime, then that is fg prime plus gf prime. That's the product rule. That's the product rule. The product rule is quite simple. You got to take the derivative of one of them multiplied by the original of the other. And you got to flip it. Really, order doesn't matter with any of this stuff, does it? Because I've got multiplication and addition. I could say f prime g plus g prime f. I could say g prime f plus f prime g. I could reorder here and it won't make a difference, right? Because I've got multiplication and addition. I'm saying that because it's important to note that while the commutative property exists in here, in the quotient rule, it does not. We can't change the order. We have to be very specific about the order. Okay? But in the product rule, it doesn't really matter. Fg prime plus g prime f. Oh, sorry, fg prime plus g f prime. Got to have the derivative of each one. Like this one has the derivative of g, this one has the derivative of f. And what is it multiplied by? The original of the others. Now, the hard part about this is being able to tell when you have to use it. Right? How do you know when you need to use the product rule? Well, you need to use the product rule when you see two different types of functions multiplied by one another. Okay? You do not have to use the product rule when it's just a constant multiplied by the other, but you do need to use the product rule when it's two different types of functions multiplied by one another. For example, take a look at this. We've got our function is, f of x is x e to the x. Do you notice how we've got two different types of functions? We've got a linear and an exponential multiplied by one another. This is a basic example of the product rule. Okay, so that means f prime is going to be, okay, so this is our f and this is our g. So this is going to be, again, how do we write it before we wrote fg prime plus gf prime. So this is going to be f times the derivative of g. Well, what's the derivative of e to the x? E to the x. Our good friend, the one that's so simple. Plus, okay, we got g f prime. The original g, e to the x, times f prime. What's the derivative of x? Just 1. So there it is. Let's reduce it down a little bit, right? Can't I factor out an e to the x? So let's do that. So x plus 1. Okay, that's the first derivative. Part B says, okay, let's take that and try to expand it. Find the nth derivative. Well, I guess if they want the nth derivative, we should try to take the second derivative and maybe the third and maybe the fourth to see if there's a pattern. Okay. Yeah.
Why does e to the x and then the x plus 1 factor to that?
Because I have a common e to the x in these two chunks.
Then what is the x? Oh, okay.
Does that make sense?
Yeah.
Let's do that same thing. Let's find the derivative on this. Right? Do you recognize that this is a product? Being able to recognize that you must use the product rule is half the difficulty of the product rule. Okay, so now this is our f and this is our g. So we've got f, g prime. What's the derivative on g? 1, right? Derivative of x is 1. The derivative of 1 is 0. So this is just times 1. So let's just leave e to the x. Plus g times the derivative of f. Well, what's the derivative of e to the x? E to the x. And look again. Look at these two chunks. Don't I have a common e to the x again? So let's remove it. Let's factor it out. That'll leave me with a 1, because I factored that out there, plus x plus 1. I don't need to keep the parentheses there because it's just addition. So all said and done, e to the x, x plus 2 is my second derivative. Let's, for good measure, find the third derivative. You might be able to already tell a pattern. You might be able to estimate what you think it's going to be, but let's find the third derivative. Okay, so now this is our f, and this is our g. F, g prime is our first term. E to the x times, what's the derivative on x plus 2? 1. Plus g f prime. So g is x plus 2. F prime is e to the x. And again, we can factor out an e to the x, which is going to be 1 plus x plus 2. Or in other words, e to the x, x plus 3. So what do you think you can make as a statement about fn of x? What's always constant? E to the x, and then we've got x plus n. The reason why I like this example is because right now we have only really found the derivative of polynomials. And for the derivative of polynomials, it just keeps reducing and reducing and reducing and reducing and reducing until you get to 0, right? It just keeps getting smaller and smaller and smaller. Derivatives don't always work like that. Derivatives can be cyclic. They can follow patterns. They can repeat themselves over and over again, like the derivative of e to the x, right? We're going to find there's one whole section about the derivative of trigonometric functions, and that is cyclic. It just keeps repeating over and over again. I think it's like a cycle of 4. Okay. So this is a patterned derivative, e to the x, x plus n. All right, so let's take a look at this one. Now, understand that there is a way around finding the derivative using the product rule. You don't need to use the product rule here if you don't want to. I would advise against that because it's a little bit more difficult, but you don't need to use the product rule if you don't want to, because can I actually distribute that radical x in? Sure, and then you wouldn't need to even be using the product rule. Now, understand something here. When I go to differentiate this, I'm going to differentiate f of t. What's my variable? T. That means what are a and b? Constants, right? People always think of them as variables. No, they're not variables, they're constants. If it's not dependent upon the independent variable, then it's a constant. Okay, so we've got the radical t as our, I'm just going to rewrite it. F of t is equal to radical t a plus bt. It might be a good idea to, instead of keeping it as a radical, like we said yesterday, let's write it as a power. T to the 1/2 a plus bt. Okay, now let's find f prime of t. Well, I hope you recognize we must use the product rule because there's a product there. So this is our f, and this whole chunk is our g. So we've got f g prime, t to the 1/2, g prime. What is g prime? B. Good. Just b. Because I would look at the derivative of a plus bt and then say, okay, what's the derivative of a? Just a constant, right? Derivative of a constant is 0. And then we find the derivative on bt. Well, what's the derivative on t? Just 1 multiplied by its original coefficient of b. So that's why this is t to the 1/2 times b. I don't need to really put parentheses there. I'm just doing it in parentheses. Plus, okay, g f prime. Okay, f prime. That would be 1/2 t to the negative 1/2, right? So this is in essence our derivative. From here on out, we are just reducing it. Okay, so this is the square root of t. Let's put the b in front because it's a constant. B radical t plus, all right, now I've got a plus bt in the numerator divided by 2, and then I would say t to the 1/2 power down below, but let's just put 2 radical t. And I'm okay with that being our final answer. I could get common denominators, but nah, I'm good there. Questions about that? All right, let's keep on going. One more product rule. Okay, same type of thing. The notation's a little funky, but basically saying, well, I've got to find the derivative of this thing because I know I'm going to need to because I want to find f prime of 4. So let's find f prime of x. Okay, in this case, this is our f, and g is our g. So I have f g prime. And let's use x to the 1/2 power. So we've got f g prime, x to the 1/2 times g prime of x. Oh, not equal to, plus g, which is just g of x, f prime, 1/2 x to the negative 1/2. Same type of thing that we just did on the last slide. Okay, let's reduce that down a little bit. So f prime of x is radical x g prime x plus, we got g of x in the numerator over 2 radical x. Okay, let's find f prime of 4. That means this is, f prime of 4 is radical 4 g prime of 4 plus g of 4 over 2 radical 4. And we know all of these things. Radical 4 is just 2. G prime of 4 is 3. G of 4 is 2. And then we have 2 times 2 in the denominator. So 4. So this is essentially just 6 plus 1/2, or 6.5. So that's the product rule. We're going to be using the product rule a lot. Because that now, we've gotten polynomials, we can do radicals, we can do rational exponents. We haven't talked about rational functions yet. We haven't talked about trigonometric. We're doing a lot of things, but now we can say any of these types of functions, if we multiply them together, we can also find their derivatives using the product rule. So what if we divide them from each other? Well, that's the quotient rule. Now, the product rule in comparison to the quotient rule, was super simple. F prime G, G prime F, done. Move on. The quotient rule, however, is a little bit more in depth. Let's analyze the Leibniz notation and then use our notation. Okay. We got d over dx of f of x over g of x, which is a quotient, right? It's a quotient. Okay, this is saying I've got g of x times the derivative of f of x minus f of x times the derivative of g of x, all divided by the original g of x squared. Let me say that one more time. G of x times the derivative of f minus f times the derivative of g divided by g squared. So this is how I like to write it. Okay, no pen. We got f over g prime is going to be equal to g f prime minus f g prime all over g squared. That's how I like to visualize it. If you have any friends in AP Calc, they say it like this. Low d high minus high d low divided by low d high minus high d low over low squared. That's what it is. Low, which high and low mean the original functions. They're calling high f, low g. Low, d high, d stands for derivative. Low, d high minus high, d low, all over low squared. That's how they memorize it. I don't know. I just memorize this. Gf prime minus fg prime over g squared. Now, is subtraction or division commutative? No. So be careful. It has to go in this order. I guess you could change around the, like, if you want to do f prime g right here, okay, whatever. If you want to do g prime, okay, whatever. That's fine. But you cannot change the order. The g prime always must come in the second term up top. So let's work with it. Now, the nice thing about this, you're like, oh, but how do we find the derivative of rational functions? The quotient rule. Isn't a rational function anyway just like a quotient of two polynomial functions? So every rational function is just basically a division of two other types of functions. It's always a quotient rule. Now, pause for a moment and just appreciate the time that we're going to save. Like if I tried to do the definition of a derivative here, this would be like one of those problems that you had on your test where you had to get common denominators and you had to do like the x plus h plus 1 multiplied, blah, 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 blah. Like I tried to give you the most simple type of function on your test because you didn't know the quotient rule yet. Like you could go back to your test and redo that problem in probably like a minute with the quotient rule. Here's what I mean. Let's find y prime. Okay, so this is f and this is g. Okay, so we have g f prime. X to the third plus 6. F prime. What is f prime? 2x plus 1. Minus, you got a question? Minus f g prime. X squared plus x minus 2. And then what is g prime? 3x squared. All divided by g squared. Hey guys, remember all those rational function problems that we had where we always ended with a binomial squared? This is why, because it always ends up like that using the quotient rule. That h always canceled out, leaving a binomial that was always the same. Oh, I forgot to write squared. That's why. It was always ending up as that binomial squared. Now, the only thing we have to do is just kind of like FOIL these out. X to the third times 2x is 2x to the fourth. X to the third times 1 is x to the third. 6 times 2x is 12x plus 6. Now, be careful. This is a minus sign. Keep the right side in parentheses. So 3x squared times x squared is 3x to the fourth. 3x squared times x is 3x cubed. 3x squared times negative 2 is negative 6x squared. I am going to allow you to not have to square the denominator ever. I am okay if you never square the denominator. You don't really want to, because you should try to reduce down the numerator so that maybe you could possibly like factor something out of the denominator, and that's technically in factored form, x to the third plus 6 squared. So let's reduce it a little bit. I've got 2x to the fourth minus 3x to the fourth, so negative x to the fourth. I've got x to the third minus 3x to the third. Again, minus, I'm distributing in that minus. Minus 2x to the third. Looks like I should get my x squared next. Negative turns positive 6x squared. And then I have 12x plus 6. All divided by x to the third plus 6 squared. And I'm going to leave it at that. That's y prime. So that's the quotient rule. Yeah, one more problem after this. Let's do one more. See, now that we've done product and quotient rule, we can really get into the application of derivatives a lot quicker. And the reason why we do derivatives a lot quicker, because now we don't have to spend so much time calculating the derivative. Calculating derivatives are a little bit easier now that we know all the rules, so we can just focus on the fun stuff. My version of fun stuff. Right? Like finding the equation of tangent lines, you know? So cool. Ooh, just a blast. Find an equation of the tangent line of the curve y equals e to the x, our good friend e to the x, over 1 plus x squared. All right, you recognize that we've got to use the quotient rule now, right? See, I'm not going to say like, oh, use the quotient rule to define the derivative. No. You just have to know when you have to use it. Recognize that there's a quotient. So this is f and this is g. All right, so y prime is going to be, all right, we got g f prime, low, d high. What's the derivative of f? The derivative of e to the x. E to the x. Minus high, e to the x, d low. Well, what's the derivative on 1 plus x squared? 2x. All divided by low squared. 1 plus x squared squared. That's a 2. Again, I'm not going to force you to FOIL that out. My first year teaching calc, I like made them FOIL it every time. Yeah, it doesn't help anything. At that point, I didn't know if we would need to do it later on. Now I know that's just futile. We don't have to do that. All right, so let's see if we could reduce this at all. This ends up being, let's factor in that e to the x. This is e to the x plus e to the x squared minus 2x e to the x, all divided by 1 plus x squared squared. I could factor out an e to the x, but there's really no reason, because the only reason we're creating the derivative is to find out what the slope is going to be. I'm not asked to find the simplest form of the derivative. So let's just get the slope now, because that's the derivative anyway. So find the slope, and what are we going to plug in? 1. So this is going to be e to the first plus e to the first times 1 squared, which is just 1, minus 2 times 1 times e to the first, all divided by 1 plus 1 squared, so 2 squared is 4. Okay, well, what's e plus e minus 2e? 0. And 0 over 4 is 0. What does that tell you about the tangent line? It's horizontal, right? So it's y equals 1/2 e. There's the tangent line. You know, because the fact that this comes out horizontal, what is that telling you about the original graph of f at this location? If the slope of the tangent line is horizontal,
There's a max or min.
there's a max or min. Do we know which one right now? No. There will be tests later on to see, like, is it a maximum or minimum? We'll have to do, like, well, we'll talk about later. But there are tests on whether to see that it's a maximum or minimum point. It's called the increase-decrease test. That's what it is. There will be ways to figure out whether it is a maximum or minimum point at that location. But right now, all we need to know is that, well, if it comes out as 0, there's got to be a maximum or minimum value right there. We don't really know what it is yet, but we know that it's there. The last slide of these notes, I put on there, and it's PDF'd on the notes there. If you want to, like, create a list for yourself of all the derivative rules, like kind of like a running list, because we're going to create more and more as we go. Like, we're going to add on this trigonometric rules. We'll add on this the chain rule. We'll add on this to a bunch of different more rules. But I put on there, so if you ever wanted to see them compiled in one location, it is there for you guys if you need it. What's on there? Okay, the derivative of a constant is 0. This is the power rule that allows us to do polynomials. Obviously, e to the x. This is our constant rule where we just multiply by the constant. This is the sum, the difference, the product, the quotient rule. All right, let me stop the video here. Oh, don't. Oh. Got it.
Bye-bye.
Bye.
Happy Halloween.
That was Corbin.